So good morning to all of you. Welcome to the second lecture in the series on Flexure in beams. If you recall, in the first lecture we did a simple introduction to flexure in beams, what is meant by bending, what is meant by curvature, how is bending related to curvature. Now we are going to get into analysis problems where we look at how the deflected shapes are related to bending moment and shear force diagrams. You'll find that when you do structural analysis, you will need to draw these diagrams. The purpose of drawing these diagrams is to know the distribution of internal forces in a beam. If the problem is an analysis type problem, we want to ensure that the bending moment and shear force are within the capacity of the beam. And if it's a design type of problem, we want to ensure that the beam is so designed that these capacities are not exceeded. So we get into this topic. First, we will go into what is known as a simple bending theory, where we look at stresses and strains and see how bending moment causes normal stresses. We want to derive a relationship between the stress, the strain, the curvature, the elastic property, and the bending moment at the section. Next, we'll get to learning to draw shear force and bending moment diagrams and relating them to deflected shapes. We had a brief introduction to this in the last session. Some of you are senior students, you've already done lots of these things, but it's always good to see if there are quick ways of drawing these diagrams and how to make sure that the answer you've got is correct, and more important, can you draw the deflected shape and relate it to the bending moment diagram. Then we look at the relationships between the load intensity, shear force, and bending moment. So let's look at the Euler-Bernoulli theory of simple bending. There are some assumptions. The first assumption is the material is homogeneous, isotropic, and elastic. Linearly elastic, which means it obeys Hooke's law, which means that elasticity is a property which implies that when you load the material, it will deform, and when you remove the load or you unload it, there is no residual deformation. It recovers the elastic deformation. And more important, it retraces the same path, which is the stress strain path. A material is said to be linearly elastic if the stress strain relationship is linear, passing through the origin. And that is known as Hooke's law. Robert Hooke gave that law. I may also add that most materials follow this linear elastic behavior until a certain stage of loading. As long as the deformations are small, this is a reasonable assumption to make. When the deformations are large, then this assumption may not be valid, or when it's a material like concrete which cracks, then the homogeneity is lost. But even then, we can continue to use this if the deformations are small. We'll look at situations, simple problems where this assumption is valid. The second assumption is that the beam is subjected to pure bending. And this we saw in the last class. You get pure bending when there is only bending moment, there is no shear force. It is in such situations that plane sections remain plane. The correct assumption should be stated like this: plane sections in an initially straight beam will remain plane even after bending. If there is some shear force in the beam, and that is something you get when the bending moment is not constant but varies along the length of the beam, then you'll find that there will be some distortion which is called warping. We'll also look at warping later. The beam is initially straight and it is assumed that it has a constant cross section along the length of the beam. Such beams are said to be prismatic. That means the cross section is a prism and the prism cross section does not change along the length of the beam. Another assumption implicit is that the axis of bending always remains perpendicular to the cross section of the beam, and we saw the implication of this in the last lecture. It is because of this that under pure bending the deformed shape is a segment of a circle, and you can talk of a curvature and a radius of curvature. All the normal lines will converge to one point and you can draw a circle to any of the layers. The Young's modulus, which is the elastic modulus, is assumed to be identical in compression and tension. This is true in materials like steel, but not necessarily true in other materials. But this is a simple theory and it's good enough for many practical cases. So we make this assumption even in the case of concrete. The radius of curvature is large compared to the cross-sectional dimensions of the beam. That's an important assumption. So this is valid for small deformation. But most of our beams in practice, in buildings, in bridges, the deformations are small. In fact, we would feel psychologically uncomfortable if there were large deflections. Many laymen think there are no deformations at all. There's no deflection at all. But if you look at any beam closely, you'll find that it is deflecting. And not only that, a concrete beam has hairline cracks if you look closely at them. So what is this theory of simple bending? Well, consider a cantilever beam like the one shown here. And let's not assume a rectangular cross section. Let it be any section, a tapered section like the one that's shown here. If we apply a moment at the free end, and we've shown you how this can be done with the help of a couple, it's going to deform. And to maintain the assumptions, you'll find that it will curl up like this. We have seen this picture earlier. Remember when we heated the beam and cooled the beam, the bottom layers were heated and the top layers were cooled. We assumed a linear strain distribution. But that was a case where you had strain but no stress, no internal force. Here the deformation is induced by a force, in this case a moment, and the moment causes this bending, this curvature, and you can talk of a radius of curvature. The radius r of course depends on which layer in the beam you're referring to. So if you take a section at a distance a from the fixed end and you blow it up, then you'll find that it has a curvature like this. An angle theta is subtended from that center of curvature, and the distance subtended is r theta, and that for small deformations, there's one line in that section which we call the neutral axis, which will remain unchanged, and its length will remain r theta no matter what the moment is. It will continue to remain like that. You can clearly see that in this curvature, which is a sagging curvature, the layers above that chain dashed line, which we call the neutral axis, the layers above that, sometimes referred to Na, where there's no strain and therefore there's no stress, will be subjected to contraction and a compressive stress, and the layers below will be subjected to elongation or a tension. So you have normal stresses coming into the picture, and if you take any distance y above the neutral axis, you could define the change in length, and therefore define the normal strain at that location. So you define the location not only transversely as the height y above the assumed neutral axis. By the way, we don't know in advance where that neutral axis is. We are assuming there is some axis. We'll prove later that that axis can be easily located. It's a geometrical property of the section, but right now we don't make that assumption. So transversely, it's at a height y, and longitudinally, also we are saying it's at a location A along the x-axis. You will find that in a case of pure bending, it doesn't matter where that x is. The distance A doesn't matter because you'll find this bending moment is constant everywhere. But in a real beam, bending moment won't be constant, and you'll find epsilon will change not only with x but also with y. So what's the change in length? We looked at this in the last lecture also. It's simply r minus y into theta. That's the change. That's the new length after deformation minus the original length r theta divided by r theta. And so we've seen this earlier also. You'll find that the strains are linearly distributed along the depth of the section. Epsilon x is seen to be minus y because y is shown positive above the neutral axis for the sagging curvature. And so the minus sign, the negative sign, tells you clearly that you are having a compressive strain. We are making an assumption that tensile strains are positive, so compressive strains are negative. And the fact that epsilon is proportional to y, r is a constant, suggests that you have a linear strain profile. The maximum compressive strain will be at the top fiber level. The maximum tensile strain will be the extreme bottom fiber. And once you have an elastic strain, you have an elastic stress. A normal strain will give you a normal stress in such cases, which is E times the normal strain, and so you get sigma x equal to minus E by R into Y. Very simple linear relationship. So what do we conclude? That not only the strains have a linear profile, the stress also has a linear profile, and here we're talking of normal stress, the same kind of stress which you get by stretching, applying an axial tension or an axial compression. Here you have both. Layers above the neutral axis are compressed, layers below the neutral axis are extended. You have compressive stress and tensile stress, and the whole thing put together gives you the effect of the moment. So the definition of sagging curvature, which we treat as positive in civil engineering applications: fibers below the neutral axis elongate, fibers above the neutral axis contract. Now let's recall that the beam is actually three-dimensional, and here's a three-dimensional picture of the beam. You can see the linear variation in the stress. It should be compression on top and tension at the bottom. And actually, we said it's a function of y, which means in the z direction, in the breadth direction, all layers, all points will have the same strain and same stress. That's a fundamental assumption we are making. So it's actually an entire surface which is getting affected, and so it's a neutral surface. That's the correct word to use. And so the word neutral axis can be used to any axis on this surface, either longitudinally or transversely. It doesn't matter. Sometimes people refer to the z-axis located at this origin as neutral axis, and some people take the longitudinal axis. You're actually referring to a plane. And the fundamental equation which we've just derived is sigma x is equal to minus E by R into 1. Let's take a small element dA. And the stress in this element is sigma x. And we know even beforehand that if y is positive, this element will be subjected to compression by the definition of this equation. And if dA is located below the horizontal neutral axis, it will be subject to tension. We want to now derive relationships, and we'll do it from fundamentals. Let's look at the equilibrium of the whole section. If the beam is in equilibrium, every free body of the beam must also be in equilibrium. And so the resultant force, in this case it's only normal force, horizontal force, must be equal to 0. Please note that when we do structural analysis, we actually write these equations with reference to the undeformed geometry. So it's still horizontal, though actually it's curved a little bit. That curvature is very small, so we still pretend it's all in the x-axis. But it is stretched and contracted. So if you plug in the value of what is fx in that element, the fx is sigma into dA, which we need to integrate across the entire area of the section, and that's what we'll do. So the net axial force, normal force, in this case horizontal force, must be 0. That is equilibrium. If you substitute the formula for sigma x, you will get it in this form, and you can pull out E by R outside the integral for the simple reason that it's a constant. Modulus of velocity is a constant. The radius of curvature is also assumed to be a constant. And so in an equation like this, E by R obviously cannot be 0. And so integral y dA must be 0. And so A is again, you can take the centroid of the area. That's how I'm sure you studied properties of areas. So y bar is some distance that we say is locates the centroid of the area. So y integral y dA can be also written as y bar A equal to 0, where A is integral dA. Now A obviously cannot be 0, so y bar equal to 0, and so you come up with a simple proof that the neutral axis is that axis which matches with the centroidal axis. It's a very fundamental definition. Don't forget it. It's a property of a beam, and so it's a property of this geometrical property of the cross section of the beam, y bar equal to 0. That's the first important point that emerges from this equilibrium. Now let's look at the effect of bending moment. We know that the body is in equilibrium, so there must be moment equilibrium. We are talking of bending or rotations with respect to the z-axis, right? And so if you take the equilibrium of that body, you could write it in this manner. M is the bending moment at the section, and that minus, now we'll take the force and the distance of the force from the neutral axis, which is y. So we could write it in this way. If you substitute for sigma x, you'll find there's a y squared term that comes out. So we are finding the moment is equal to E by R into integral y squared dA, and that is the definition for the area moment of inertia with respect to the z-axis. And so what do you learn from this equation? You learn that M is equal to EI by R. M is equal to EI by R. And EI property is sometimes referred to as flexural rigidity. It's a product of the elastic modulus, which is a material property, and a property of the cross section, which is I. So we come up with this beautiful simple definition which relates bending moment to curvature. Curvature is 1 by R, as we saw in the last class. So that's completes this definition, and of course we note that there's a plus or minus that you need to know to bring the stress. If y is positive, sigma is negative, and if you combine all these equations, you get an equation worth remembering, and I think many of you know this by heart. Sigma by y is equal to m by I is equal to E by R. Sigma is the normal stress, tension or compression depending on its location above or below the neutral axis. Y is the distance of the point above the neutral axis or below the neutral axis. M is the bending moment at the section. I is the second moment of area, sometimes called moment of inertia. Please note there's another moment of inertia which is called the mass moment of inertia. So it's an area moment of inertia or second moment of area, and E is elastic modulus, R is the radius of curvature. Now you could go ahead and see that sigma is maximum at the two extreme fibers. If the beam is subjected to a sagging curvature, sigma max will be compression at the top and sigma max will be tension at the bottom. So there's a third equation that emerges because we are now saying it should satisfy all the equations of equilibrium. Now this equation is normally not understood well by students, so I want you to pay attention. We are now saying the moment not only with respect to the z axis should be equal to 0, but it's also with respect to the y axis. Now if you understand clearly what this means, you'll find that if you substitute here sigma x equal to minus ER by y, you're getting an interesting requirement, that is integral yz dA equal to 0. This integral y squared dA is second moment of area, integral yz dA is called the product moment of inertia, which you may have studied. Well, in simple bending theory, it turns out if you want to use that formula m by I is equal to E by R equal to sigma by y, you also have to make sure that the product of inertia term is 0. That means you must choose your y and z axis, they are known as principal axis, in such a way that this is satisfied. Usually this is satisfied in symmetric section. Okay, so for simple bending theory to be applied, the axis y dash is y horizontal dash and z dash should be so defined that the product moment of inertia is 0. Okay, the same y and z. So you'll find that in a rectangular section, tapered section, T section, I section, the symmetry with respect to y axis is usually satisfied. But in a channel section or an angle section, which you use commonly in steel, it is not satisfied. What does this mean? This means if I load this, let's say the beam is like this horizontally and I load it vertically, it's not going to just bend vertically. It's going to bend horizontally also, because it's going to bend about, it'll have components both about z and y axis. Such bending is called unsymmetrical bending. You need to study that separately. We don't have time to cover it here, but the major concept to understand is if the loading is in the same direction as the principal axis, in this case y axis, then bending will occur about the perpendicular axis ZZ axis. But if not, the bending will occur unsymmetrically with components along both the principal axes. Axes, when it's written in plural, is AXES. When it's singular, it's AXIS. Now let's step back and see all that we've learned. Axial member we all know. So the measure of strain and stress are epsilon is E by L, sigma is Nx by A. Everybody knows this. We looked at it in the last session. The corresponding expression for strain and stress in a beam, which will be minus Y by R, so it's something to note. Again, please note it's non-dimensional. Just like E by L is non-dimensional, Y by R is non-dimensional. But it's a new term for many of you. You have to get comfortable to this. You have to know that without R, you don't have strain. So it has to have curvature. A straight beam will not have a finite value of R. So if R is infinite, epsilon is 0. So R has to be finite. It's very interesting. If you look at this cantilever beam, this R is constant everywhere. Okay, it's a perfect segment of a circle. But in a normal cantilever beam, let's say subject to a concentrated load, you'll find that the radius of curvature varies along the length, and the maximum curvature, maximum bending moment is at the support. And you can see the expression for stress is bending moment into y by I. So if stress is maximum at the support, strain is maximum at the support, radius of curvature is minimum at the support. And radius of curvature, because bending moment is 0 at the free end in a cantilever, you will find that the radius of curvature is infinite at that. So if you were to draw a circle, you'll have to draw lots of circles with different radii till the radius becomes infinitely large. So it's a good question that many students trip over. Where is the radius of curvature smallest in a cantilever subject to a constant load at the free end? The radius of curvature is smallest at the fixity location, or you could say the curvature is maximum because 1 by r, and curvature is related to bending moment, and the radius of curvature is infinite at the free end, or you could say the radius of curvature is 0, 1 by r. So this is the constitutive relationship. Now, often in practical design, we are not interested in the variation of stress across the depth of the member. We want to design for the worst stress. Please note, an axial member is structurally more efficient than a beam. Why? I think I should have a dialogue. An axial member, in an axial member, the material is fully utilized, but in a beam, it's not fully utilized. You're actually wasting the potential of the cross section being fully utilized. Can anyone give a reason? Any answers to this question? I have a member. If I pull it or push it down, the entire cross section is utilized, but if I bend it, I'm not fully utilizing the cross section, the material. Could be steel, could be timber, not using it. So it's structurally not as efficient as a bending creates this lack of structural efficiency. Can anyone explain why? Simple answer. Okay, we cannot afford to wait, so I'll give you the answer. The answer is, at the neutral axis, the material is not at all being used. There is no strain, no stress. The capacity of the beam is tested at the extreme fibers. In between, it's not fully utilized. So we are actually wasting material in a certain sense. That's the first point. We'll now look at a concept of section modulus. Let me pose a question to you first. If I take a ruler, a scale, and I bend it, is it easier to bend along the thin direction, along the stiff direction? I wish I had a scale here to show. This scale, can you see me, is easy to bend like this. I hope I won't break it. But it's very difficult to bend like this. Why? This scale is easy to bend like this, difficult to bend like this. And it's elastic because once I release it, it's back to the horizontal, right? But this, I can't even bend it. Actually, I can, but it's so small, I can't see it, you can't see it. Why? Same material. Any answers? Yes? Okay. You could be asked this question in an interview for a job. No answers? Then I'll give you the answer. Okay. Let's take a rectangular section. Okay. Let's say the depth of the section is 3 times the width. We have the option of bending it along the major axis, and we have the option of bending it along minor axis. Okay, major axis is this. It will bend about this axis, or it will bend about this axis. Okay. In this case, the width is A, the depth is 3A. Here, the width is 3A, the depth is A. You will find that the deflections, the curvatures will be much less here compared to this. This will bend more easily. So the question I'm asking you is, let's say both are made of some material, and the material has a certain capacity given by sigma allowable. tell me which will take more load, more moment, this section or this section, and how much more. You understand? Let's say there's some allowable stress sigma max, say 200 megapascal. Material has that property. If you put the beam like this or like this, there's a difference. We know that this is going to be stronger. It will take more moment. This will take less moment. How much? How much more? So to do that, there's a nice property. Any answers? Okay. To do that, there is some, there's a property, and that property is called section modulus. If you look at the relationship between sigma max and m, it is sigma max is m into y max divided by I. Of course, m and I are about with respect to some z axis. This I by y max is a section property. Please note, I, second moment of area, has a units of millimeter raised to 4. Area has a unit of millimeter squared. This is integral y squared dA. So it is got the units of millimeter raised to 4. Z, capital Z is the definition, is the symbol used for section modulus. It is I by y max. Okay. Now for a symmetric section like this, y max is half the overall depth, 3a by 2. So this property I by y max has the units of millimeter cubed. So if you have a simple relationship, this is called the section modulus. Sigma max is m by z. Very easy to remember. Sigma max is m by z. So all we need to know, if both the cross sections have the material with the same sigma max, then we can figure out how much time more the capacity, the bending moment capacity will be. So for both the sections, sigma max is the same. So MA by ZA, A is the first section, B is the second section, must be equal to MB by ZB. So we need calculations of ZA and ZB. Now Z is I. I you can prove. Okay, we don't have, you probably studied this. Integral y squared dA for a rectangular section is given by BD cubed by 12. B is the width, D is the overall depth. BD cubed by 12. It can be derived. You should derive it. It won't take you any time, but let's skip that step. Y max is D by 2. So Z works out to be BD squared by 6. So D is more for section A, 3 times more, but B is less, 3 times less. So that's a trade-off. So ZA is width A into depth 3A the whole squared by 6, you get 3A cubed by 2. ZB is width 3B into depth A the whole squared by 6, you get A cubed by 2. And so you find that just by looking at the two sections, the section modulus of A is 3 times the section modulus of B. And therefore, it can take 3 times the bending moment, 3 times the load, because bending moment is got a linear relationship with the load. So it's 3 times stronger. Here's a picture that we picked up from the net. You can see that the deflections are more, it's going to bend more if it's put the other way. Here's another case of a cantilever beam with fixity at one end. You can see the deflection, but if you flip it over, you can't see any deflection because it's so stiff. So there are two benefits by making a beam bend about its stiffer axis. It's the two benefits are: one, deflections are much less. Secondly, the load bearing capacity is much more, and the ratios can be calculated. Okay, how to calculate deflections we'll cover in the next third lecture. We won't do it now.